started recording. So again, just let me repeat what I just said for the recording, for the sake of recording. So today we're gonna review what we learned in this first half of this quarter, and essentially we'll solve the last year midterm. Hopefully it will be illustrative enough so we can, as we go through the exercises, I can answer questions, and then everything will be clear by the end of it. But again, just let me go over logistics one more time. So on Wednesday we will have our midterm, right, at exactly the same time. So it's during our regular class time. It will be posted on Gradescope. So it will become available at 5, and you will have 1 hour 20 minutes to finish it, right? So don't forget to submit. Don't run out of time. It's open everything exam. However, I ask you not to collaborate with other people and not to ask for help, right, online or in person. That's about it. But you can use calculators, you can use anything you want, you can use computers, you can use GDB, you can compile programs, you can use the books, which are like anything what helps you to answer the questions, right? Rather, because again, the goal is to test for actual knowledge, not for any kind of memorization, right? So if I ask you to create a call site for this specific function, if you're so smart that you have to cheat to essentially invoke the assembly and copy the assembly from the obj dump, that's okay. But I hope that you are good enough that if you can do that, you can answer the same question equally well, right, without this. So are there any questions about logistics? All good? So let's take a look then at the last year's midterm, and let's try to solve it. So did anyone tried it already? So last time it was 2020 spring, and we can take a look at a couple of them. Okay, it's not that okay, let's start with this one. So let's copy this question and essentially just start solving it. Or I can actually maybe even annotate on this one. Let me just quickly double check. Yeah, that's good enough. So let me just download and I will be working with this. Let's just go. It was wrong. And this is wrong too. So, okay, here question number 1. So write a program that uses the Unix system call API as described in chapter 0 of the x86 book. Assume that you are writing an x86 program, and we didn't work with x86. So this year, like last year, the midterm was a little bit later in the year, right? In the quarter. And so people already booted x86 a couple of times, so they are familiar with what x86 is. But essentially, it's the same set of system calls which I was teaching in class. So you can, this time I will just ask similar questions, but we'll be saying Linux system calls, right? Assume that you're writing an x86 program so that you're limited to x86 system calls, and you call it what? Fork. The program should read bytes from the standard input. Read bytes from the standard input. Fork. Execute itself with exact fork. Self. And redirect all bytes it reads to its child, creating an endless pipeline. Okay. So what do you think? Who can write this program? Any takers? Do you understand what needs to be done here? it's a little bit a little cryptic, right? But in reality, just this is the way to solve it. So you say, look, what he asks us to do is he wants a program which reads everything from standard input, right? So essentially, this is the instance number one, main number one, right? You can see the screen well, read standard input. So it forks, right? So which means that you will have instance number two. But instead of continuing running after fork, what I ask you is I ask you to exec, right, into the same program, right? So kind of like starting executing from main, right? But what before doing this, essentially, we want to essentially redirect the standard output to the next instance, right? If the system call to fork a process is fork and the program is called fork, will there be an issue? No, there will be no issue. Why is that? Who can tell me? That's a great question, actually.
The names of system calls isn't defined based off of the file name, right?
Right, exactly. So
It's a separate
in fact,
API.
right. And of course, like I'm glad that you know the answer. That's good. But I mean, we will in the second half of this quarter, we'll cover how system calls are implemented. And essentially what's inside exec is that you invoke an interrupt and you passing like specific interrupt number, let's say maybe it's X40, right? And the specific system call which you're trying to invoke will be like, for example, pass inside the EX register. So you say, for example, EX number 8 is the kernel will invoke fork, right? That's how it will work. And when you do an exec, and here you say something like, I will exec into fork, and maybe it's something like bin fork, if you like. What happens here, exec is actually goes and searches this file name of the program on disk, starting from the root, then looking into bin, then looking for fork inside bin. And this is where it loads the program for, right? So the system calls itself, system calls themselves, and the names of the programs are kind of like two different namespaces. So they don't overlap. But again, I appreciate the question because it seems trivial, but at the same time, you know, it's always nice to confirm, right? So any other questions about what needs to be done here? Should be forks. English is a little broken here, so but should read input fork execute itself. So okay, so how will we, who can tell me like what this program will look like? Imagine I will insert a page here, page after. So remember what needs to be done. Let me just again copy this diagram. So who can tell me, let's write it together line by line. And let's just make sure that we can recreate this program. So this is our goal. So what will be the first line after main?
Probably some sort of dupe or close and dupe.
Okay. What are you trying to do here?
We need to redirect our standard in to the child standard in, or
right.
Yeah.
But don't forget, so the program reads everything and writes, like maybe it's underspecified here. The program should read bytes from the standard input, execute and redirect all byte it reads to child reading, right? So definitely you need to fork because the program itself will end up with some kind of a infinite loop, right? Because it will be, this will be the infinite loop, which will be like read 0, right? Standard input will provide some kind of a buffer, or can provide the size of a buffer right here, right? Let's forget about the error codes, but this is, assume errors are not happening. And whatever you read, you write back to 1, right? So you say buff, and again, size of buff. Agree with this? Maybe it makes sense to unmute yourself and talk because it's a little hard for me to read. Yeah, so I mean, but Shane, I think it was you because I recognize your voice, right? Do you agree with this logic?
Yeah,
So-
sorry, I was just thinking. I guess I was interpreting the question as like you set up, you don't do anything. I was getting lost in recursion. Like you don't
Yeah,
do
me
anything in
too.
main, you just hook it up to the child and there's no bottom where it ever actually would read if you do
Yeah,
it that
but-
way.
Yeah, and but the idea is to create this infinite pipeline, essentially. We can say maybe it should be done like 10 times or something, right? If you pass an argument or something, but the idea that each program is essentially reading its input and writing to its standard output, right?
Mhm.
But with this in mind, okay, go ahead. Someone has a question?
Are we writing, is it required to write to standard output, or can we write it to standard input again?
No, you have to write a standard output. But you have to redirect your standard output to the child's standard input, right?
What happens if
So-
you write to standard
Okay.
in?
What happens?
It's a
if you
bad
write
file
it?
descriptor, or will it do nothing? Or
No,
We can read it from standard in, and once we are done with reading, we fork it and write it to standard in again, and exec. Does that work?
I don't think you can legally write to standard in.
no, Shane, let me just quickly answer this one. It depends on what the standard in is connected to, right? So if it's connected to the console, zero is connected to the console and one is connected to the console and two is connected to the console by default, right? So I believe in this case, you can read and write into standard input, right, in x86 and in Linux as well, although maybe there is some kind of a standard which says something about it, but I don't think so, right? If it's, however, connected to a pipe, right, and if it's only a read end of the pipe, so read, right, and a write end of the pipe is not connected to zero, right, then you will only be able to read from standard input, right? Because if you try to write and it's a wrong end, x86, for example, will just return you an error, right? That's why typically you would assume that, okay, the way it works is that pipe has read and write ends, and the right end of a pipe is connected to your parent, which will be writing into the standard output, right? In one, it goes into a pipe. So for example, it writes some bytes, they get cached in by the pipe in an internal buffer. You read from this pipe, right? But you will, if you try to write, you can, but it will be just an error. And what you will be doing instead is that you will be reading from zero, but writing to one. And hopefully that this one is connected to something meaningful, like the right end of a next pipe, right? You agree? Although technically, if zero is a file, you will be able to read and write into a file. So nothing will prevent you. There is no, I mean, again, depending on how this file is open. So when your parent, whoever creates, you might open a file in read-only mode, and then you will not be able to write, right? But if it's the file is open in a read and write mode, you will be fine writing in standard output if it's connected to such a file. Agree? Or is there anything what is confusing still about it?
So in the question, we have to create a pipe. It's just
in the question, like, since you want to create this endless pipeline, it should hint you that you should create a pipe, right? So, and this is what Sean started with, right? So he said, okay, look, we want to create a pipe. So essentially, you say something like pipe passing, I don't know, P or whatever, P0 and P1 as arguments. And you don't have to be perfect. If you don't remember that you have to pass those ampersands, that's okay. Like I don't remember myself, but you create a pipe, right? Because then this pipe will be accessible in a child and in a parent, right? Then it's okay to fork at this point, right? From fork, you definitely need a return value, right? Because you want to see whether you're in a child or in a parent, right? And inside the child, inside the parent, if ret is not equal, I mean, you can check for errors. I mean, I will appreciate it. Not equal to 0, that's okay. You say, look, I'm done. What I will be doing now, I will be doing this infinite loop, right? I will be doing this infinite loop. The question is like, do I have to close any file descriptors or anything, right? So you say, look, my standard, I just created a pipe, and now I want my standard output to be connected to this pipe, obviously, right? So what you say is that you say, close my own one, right? Agree with this? We can put, then you say dupe. This is, I think, a read end of the pipe. This is the right end of a pipe, but okay, if you flip them, it's fine. So you say, I will dupe P1, right? Because this is the right end of a pipe, right? And at this point, you say, look, and I want to be kind of careful, so I will close both P0 and close P1, right? Does this look correct to you? And in the after that, you will just enter this endless loop and start running, reading bytes from the pipe and writing bytes to a pipe, which is connected to standard input and output, right? Agree or disagree? Doesn't close P1 before the write calls send and end of file. No, because look, you duplicated it, right? So you did a dupe. So at this point, let me just change the color. At this point, the pipe will have, since you duped the right end of a pipe, so it's both connected to number 1, and it was connected to both whatever was returned, but read and write. Let's assume it's number 3, and this, if it's a write, so maybe number 4, and if it's a read end, this is number 3, right? So you're closing these two, right? But this one, the 1 is still open, right? Agree with this, Dominic? Okay, everyone gets what's going on in this program? So this is inside the parent, right? Okay, go ahead.
Can you please explain the close P0 and P1? You said to be safe, but can you please elaborate on it?
Yeah, so why to be safe? I mean, yeah, it's a loose phrase, I agree. Meaning that if the parent will, like, imagine the parent, the very first program, maybe will send only 1 byte through this pipeline. The pipeline itself is evolving, right? But since it's 1 byte, obviously, when you say, look, I'm done reading here, technically speaking, it shouldn't be an infinite loop here. It's like kind of an interview question. So you will have to provide some kind of a condition, and you say, if kind of like done here, right? You say, while not done, right? I will be doing that. But the moment I'm done, you obviously want to exit, right? And this way, actually, you might read 1 byte, write 1 byte into a pipe and exit, right? And then this, you know, depending on how operating system will schedule you, maybe this chain will be kind of like propagating forever. I don't know if it will ever stop, right? Depending on how you schedule, like maybe, you know, the parent will always be closing before the child will be starting, or the child starts, but it doesn't execute, the parent closes. And so the whole chain reaction will last forever, right? But in order to get this done, I'm coming back to your question, in order to get this done, all the ends of the pipe, right, essentially in the child, right, they have to be, and in the parent, they have to be closed, right?
I got it. Yeah. So it
Because
has to.
otherwise, it will be waiting for more input.
Yeah, you have to flush before it can be read somewhere else. Got
And
it.
okay, if you're asking me, so where is this flush? So I'm reading, okay, and I'm writing this, and at this point I'm done, right? So at this point, since you're done, and you exit, right? This last end of the pipe will be closed. Whoever is connected, the child which will be connected to this end of the read end of the pipe, will get notified that, okay, there will be no more bytes read from a pipe. It was the last byte, and the child will, in the very similar manner, will also retrieve this error saying, okay, we read everything. Read returns 0, so there is nothing else to read, and it will also exit, right? You got it?
Yes, I got it.
Okay, thank you. Everyone else?
Similarly, yeah.
Yeah, it's a very good question, actually. So everyone else got it as well? Yeah, okay, good. So, okay, we got this part. So this is, but again, look, I'm like you. I look at this midterm, I literally don't remember anything. I just have the basic knowledge about this system calls. I'm a little bit even scared that I will not be able to solve it, right? Because, I mean, I looked at it, but very, very briefly, but I use logic. So first of all, look, I instead of getting scared, I draw a diagram, and it took me 2 diagrams to understand what's going on. This was diagram number 1, right? So I quickly summarized what is it we are asking, right? Then I drew another diagram, which kind of explains how this evolves, like you fork, right? It helped me. And then I started coding. And I mean, I'm not very good at interviews because I'm not prepared for them, right? So it's you who have to be good, right? Not me. I don't have time to prepare at all. But I started like from a child because it's easy for me to write. And I actually started backwards, right? So I started backwards. I said, okay, I will write this core because I know that this is what should be happening. Then I understand that I need to pipe. I understand that I need to fork and stuff like that, right? So you do the same. So just don't get scared. Don't let the complexity kind of overwhelm you, right? It's not as hard. Just draw the diagram. Pipes are inherently simple. I'm not going to ask you like to do some, topology of a star or anything with pipes, right? What's going to be the submission format for the midterm? Will it be done through the grade scope similar to the quizzes? Correct, right? But this is an open question, so you have to type it into the text box and actually say, look, this is the answer, plus some explanation and comments and stuff like that, which are allowed, right? Right? Okay, wait, we didn't finish. So this is the child. We still need to understand what happens in the parent, right? So in the parent, we say, look,
Wasn't this the parent?
Say again?
This was the parent, right?
Oh yeah, yeah. This was the parent. Sorry, like what happens inside the child? So now the child, yeah. Inside the child, this condition will not be true, right? We'll never reach the exit, so we'll execute it. Like here, we should say, okay, if you really want to pass a very good interview, and people will probably appreciate it, you say if ret is less than 0, you say print to standard error forking, right? And at this point you say I exit as well. Why not to do that? It's easy. But here you already know that you're inside the child, and you say page, new page after, and you say, look, what do I have to do inside the parent? Who can inside the child? You say child.
We open the readend and then dupe the readend from the pipe.
Yeah, so we need to redirect standard input to this pipe, right?
Yeah.
So close standard input, yeah, so close 0, someone tells me, Dominic, dupe, correct, dupe pipe 0, correct. Now this pipe is connected to standard input. Now we have to close our bodies P0 and close our bodies P1, right? And at this point, correct exec into whatever it is, exec into fork. That seems correct to me, right? And that's it. I don't see anything else. Maybe there is a mistake, but it looks reasonably right to me at this point. Okay, got it. Any questions? And of course, you should understand that this exec into fork will start the child from main, and main will again start yet another pipe, which will be a connection to its child, right? But it will be reading those things again from in this infinite loop, right? All good with this? Any questions? Okay, let's go to the next question then. Again, don't get scared when you look at it. Yeah. Okay, imagine you break right on the printf line below. So you break in GDB here, right? In the following x86 program, again x86, but let's say Linux, specifically write on the call instruction that is about to call the printf function inside the bar function. Okay, so we're actually breaking right when you say call printf, right? Please draw the stack and explain every value on the stack. Assume that compiler does not use stack alignment, but maintains stack frames. You can make up any values for the return addresses. Okay, so I ask you to draw the stack. Okay, so how do you go about it? You say, look, how does this program really start? It's an x86 program. In Linux, maybe something was executing before main, but maybe if I'll ask this question, I say, look, main was the very first function which executed. No dynamic linking, nothing like that was running. Nothing was running before main. Main itself executed foo, right? So let's start drawing the stack. So we say, look, imagine main is at address main was actually invoked by the operating system kernel, right? So there's a couple of issues here. So one issue is that imagine stack goes down. You say, look, main was running. The question, like, did we have any arguments to main? Main seems to be a void function here, but it doesn't mean that, operating system doesn't follow the calling convention for main and doesn't pass some arguments on the stack. We don't really know about it right now, right? So you say, well, let's forget about it because it might be a little bit complicated, right? But we say if we don't have time, we'll come back to it. So this instruction has something like call foo, and foo has 3 arguments, right? So remember the calling convention. So we have to push those arguments on the stack. So something what was happening was push 1, push 2, and push 3, right? Main doesn't have any local arguments, so nothing will be on a stack here, right? However, most likely, and again, you might not know this, in order to preserve the calling convention for main, right? Hold on here. Since we said, first of all, we said that main itself, the compiler maintains the stack frame. So when we entered main, right, the sequence inside main was push EBP on a stack, right? So something like that EBP was pushed on a stack, right? And we also pointed the EBP to point right here, the new EBP, right? In order for the main to access its arguments, the operating system will push some dummy return address on the stack itself. Otherwise, instead of accessing argument like this, right, it will, the code itself generated by the compiler should be using something like move EBP, which points right here, plus not +4 but +8, right? Agree with that, into like some register. That's to access argument arg1, right? This is arg1. So if we don't put this on the stack, right, this dummy value, then the code generated by the compiler, and the compiler doesn't really know that main is some special function which never really executed, like nothing, never got called, right? So it will instead be accessing argument arg2, right? Agree with this argument? Did you get what I was trying to explain here?
There's no return address that would be on the stack when you're in main, but the compiler still generates the offsets as if it was there. So you need to put something there.
Correct.
Okay.
And so operating system, and we will see that later, Operating system will put something here, right? Some dummy value. Actually, null is a good value, right? Just so the compiler, if main takes arguments, and normally main does take arguments, right? So it can access those arguments. And we didn't cover this calling convention for main, but essentially it takes an array of pointers to the arguments, right? So it's this arg vector, right? And the last element is 0, right? But those are pointers to other arguments, which are often allocated on the stack as well, right? So typically, the first argument, the name of the program itself, in our last example, it would be fork, right? So that would be a string. And then if fork takes any arguments, then they will be pushed on like in this manner. But if not, at least one argument is always pushed by the operating system. That's the convention on Unix as well. I didn't cover it yet, so don't worry about it. So you don't have to worry about it. But if you put a null here, that's an extra point, right? And then if you say, look, I don't really know what arguments main takes, but I will, like, if it takes any, I will put them like this: arg1, arg2, arg3, right? That's a good enough explanation, right? You got the point here? Now we're getting back to this push values, right? So we say first push 3, then we push 2, and then we push 1, right? Because that's how the arguments are pushed. You agree with this? Any questions? Yeah, Justin, thank you. Now, okay, this call invocation itself, right, pushes some return address. Imagine this is B, and like make up any address, OX, whatever, say B, and you can explain me what B is, right? We'll land on foo, right? Foo itself maintains the calling convention, so it will push EBP of foo, right? Or it will be EBP of main because it's an old EBP, so it will actually be pointing right here, right? Again, no local variables here, right? But we still have to do this invocation of bar, right? And bar takes 2 arguments, a plus b and c, right? And you can say, look, okay, we're going to follow the calling convention again. Let me add a page here. We're going to follow the calling convention. So let me continue right here. And we will push what these values are. So a plus b, in our example, a is 1, b is 2, so a plus b is 3, obviously, right? So you push 3 on a stack. And then you say, what is c? C is 3 as well. So you push 3 on a stack as well. Right? At this point, you say, look, I'm going to perform this invocation of bar. So the return, should you push 3 first? You're right. Who's that? GQ. Good catch. You get an extra point. If you ever will be in trouble between 2 grades, say, okay, I pointed you to this bug in when you were reviewing the midterm, and I'll be lenient and I'll go up. You're right. So we first, absolutely correct, and I appreciate this correction. So I'm wrong. I was rushing, and I say this call side will be push C and then push A plus B. So the order doesn't matter. It's still 3, but yeah, he's right saying, or maybe it's she. I'm sorry, I cannot really see who. I don't know. I cannot judge the gender. So you push C first, right? So it's 3, and it's nice. So you can say, tell me C, and this one is A plus B for extra points, right? So, and this is A, this is B, and this is C, right? Got it. And then actual invocation, so return address. I mean, I don't know, maybe it's return address, then old EBP again, which will actually point you to right here, right? Because this is how it works, right? And now you are actually inside bar, right? And this is where it gets a little bit tricky. So you say, please draw the stack and explain every value. Assume, okay, write on the call instruction that is about to call the printf function inside the bar function. The tricky business is printf is a variable, uses a variable argument convention, right? Let's just in this example, forget about it and say printf is not using var arg because I never covered var arg. So I should actually get rid of printf and use some other function, right? But in order for this printf to work, we say, look, what are the arguments there? Let me just copy this line so we have it in front of our lines, in front of our eyes. And then I will ask.
Are we assuming static linking because it needs to resolve printf and then we have to do things for that as well, right?
Yeah, we are assuming static linking, and I didn't mention this explicitly, but xv6 uses static linking. Yeah, but let me ask you a different question. Like, why would you say, what do you think will change if we don't assume static linking? Imagine it's a position independent code and we are actually going through PLT.
We have to do that push a function, another dummy function call to get the return address and then get it.
I agree, but hold on. But do you understand the fact that by the time we get to this line which I'm talking about, which invokes printf, the code will be the stack will be absolutely the same, because all these invocations, they're kind of like transient on the stack. They push the value, but they pop it back, right?
Yeah. I was thinking further, like when printf needs to be resolved, we need to get a return address for print.
Yeah, we push temporarily. You're right, and you're absolutely right. But in order to reason about it, again, I assume static linking, and you can tell me here in the beginning of the answer, I assume static linking, or I assume I mean, first of all, dynamic versus static. I assume like static linking, no position independent code, no PLT, right? Okay, let me quickly answer the questions. When trying this in grade scope, can we just make each place in stack new line? Yeah, absolutely. And I will usually give you like a template, like a piece of like kind of ASCII art, which you can copy and paste, right? So yeah, you can do this. Is it correct to say that the return address pushed onto the stack is the address of the next instruction after the call invocation? Absolutely correct, yeah. And absolutely correct. And I mean, I appreciate the question, because it means that everyone else will understand it as well. So okay, so printf takes 3 arguments. So we're pushing them in reverse order. So it's x and y, right? So it's the same x and y. So what is this x and y? X and y are the first and the last arguments. So it's again 3 and 3. So we will push them here again for this invocation. So the stack will look like 3, it will be y, 3, it will be x. This will be a pointer to string, right? So it will be just pointer to this string. The string lives in the data section, right? Because this is where the compiler will put it. And we will put 1 as a standard input, right? And this is, I believe, unless I forgot something, this is how the stack should look at the moment when we are about to invoke call instruction.
Can I ask you a question?
Yeah, absolutely.
I thought if printf follows the variable convention, shouldn't it go from 1 to the string then to xy?
Yeah. And I should admit, I said, okay, let's forget about it. I don't remember the variable argument calling convention myself. If you do remember, again, I really appreciate your knowledge. On the top of my head, I don't remember how it works. I mean, and that's why I said, okay, let's not do this. It's too hard.
Okay.
So the correct thing will be like, say, my print for something and explain that it doesn't. So what is how do you say the variable argument calling convention works. I simply don't remember it.
If I remember correctly, it should go from left to right, which is 1. I mean, if I'm wrong.
And then you have to pass the number of arguments somewhere as well, right?
That I don't know.
Yeah, so Dominic says, okay, but this is a great question. Just make sure that you know that this thing is there, var args, and I didn't want to overly complicate this class, so I skipped it, but it's there. But other than that, and I agree with you, so it makes sense to quickly run. I don't want to waste time right now. I would open Wikipedia, quickly read on this, but let's just get to other questions. So is this one clear to you?
Excuse me.
Yeah, absolutely.
So if there are local variables in the main function, how would they be pushed in the stack? Could you please
Yeah,
tell?
they would
I
be.
think it'd be left to right, but could you tell me how it would be represented in the stack? The local variables.
You're asking the order of the local variables on the stack. Is that what you're asking?
Yeah, in the main function.
Yeah, so someone was asking this on Piazza, and I looked it up, and I think there is no convention about the order. In fact, even compilers, like even if you see code like foo and something, and there is int a, the compiler is not really obliged to allocate space for a on a stack. It can allocate a like in a register in EBX, for example, and then nothing will be pushed on the stack. But in this class, we can assume some optimization level 0. But again, you say there is int a and there is int b, for example, and it apparently, from what I quickly read the day when I was answering this on Piazza, I think that the conclusion is that there is no convention. So the compiler is free to allocate this space anyway it wants. There is no convention because it's not part of the calling convention. It's just it's part of how compiler wants to generate code. Does this help?
Yes, but how would we be representing the stack if there is a function call after that? Like if in this question only, could you please scroll up?
Yeah.
Yeah. So in the main function, we are calling foo.
Yeah.
So just just before foo, if there are two like local variables a and b, how would we represent it in the stack? Like what would be the position for that?
Yeah. So what would be correct answer? You would say, okay, cool. Let me just copy it and like redraw it separately, this part of the stack. So I would again, I'm very reasonable person in terms of grading because the thing is that, I mean, my goal is to kind of like force you to learn stuff, not to like just catch you not knowing something. And I would say that you can draw something like this and say, look, I understand that, okay, there will be two local variables, let's assume A and B, and there will be space for them, local variables. And if you draw A and B, I would be fine. If you drew something like B and A, I would be fine. And if you say something, I intentionally just leave me a comment. I say compilers, like I see that there are local variables, but I believe that since they're used in such a trivial way, they will be allocated in registers and there will be nothing, no space on the stack allocated for them. So all these three answers will be correct.
Got it. Thank you.
Mm-hmm. You're welcome. Because this is what can happen in reality, to be honest. Okay, are we good to go to the next one? How many questions do we have? Oh my gosh. That's why people are running out of time on the midterm, right? Okay, next one. Your system has the following page table. Assume that the page directory page is at the physical address 1000. So let's start drawing. So this is the page table directory. And this is X1000. And the page table page is at physical address 2000 next to it. Page table is at 2000. And this is the content of this page directory page. We say, look, entry 0 points to 2, right? Looks like this is a pointer to 2. It's present, user accessible, and writable. Everything else is 0. So it means that they are invalid, right? The page table page, this page, contains those entries. Entry 0 as points to 3, which is the next page. Entry 1 points to 4, which is yet the page after that. So this is OX3, and this one is OX4, right? What virtual addresses and to what physical addresses are mapped by this page table? So who can tell me?
You split the 32 bits into 10 bits, and then you the first 10 bits would be ranging from 000 like all the way 0 to only 1, because there is only one entry in this. And the next 10 bits would be it would range to all 0 to, if there are two entries, so it would range from to 2. So we can concatenate based on that.
Right. So, I mean, I don't know if it's okay. So this entry, like the top 10 bits, should contain 0 always, right? Because this is the only entry which we're mapping here. And those two can either contain 3 or they can contain 4, right? So this is literally all the addresses, and those can be ranging from 0 to F, whatever, how many Fs. Let's just put ones here. 1, right? So effectively, it just maps, if this is your virtual address space, and you splice this is your virtual. This is page 0, this is page 1. So only this page 3 and page 4 are mapped, right? So only, let me use a different color here. So only these two pages, 3 and 4.
Professor?
Yeah.
Because the isn't there only because the page table has entries at 0 and 1, shouldn't the second set of 10 bits only be mapped to 0 and 1, not 3 and 4?
Correct. Yeah, come on, you also deserve. Absolutely right. So you also deserve a credit because you caught me again. Absolutely right, and I was absolutely wrong. Good job, guys. I mean, I'm proud of you, actually, to be honest. Look, I would fail this exam. So correct, that can be only 1. Oh, hold on, it can be only 0, and this can be only 1, right? So that means that only these two pages are actually mapped, 0, 0 and 0, 1, right? However, they are mapped to the following physical addresses. So if this is the virtual addresses, right? So this page number 0 is mapped to page number 3, right? And page number 1 is mapped to page number 4 in physical, correct? You believe I'm right now? Yeah, okay, yeah, good. You caught me. That's not bad. Any questions about this one? All good? Okay, more page tables. So using the same format for describing the page table as in the question above, construct the page table that maps the following virtual addresses from 0 to 4 megabytes and from 2 gigabytes to 2 gigabytes plus 4 megabytes to physical addresses 0 to 4 megabytes, where we map up to 4 megabyte. Here we map up to 4 megabyte boundary. So meaning that the page 4 megabytes and up doesn't have to be mapped. You should use 4 kilobyte page tables. Okay, so now we kind of warmed up a little bit on the page tables. So we'll start drawing what entries we need to fill in. So we say we're mapping from 0 to 4 megabyte, right? Which means that those ranges, right? Again, we will think about them like top 10 bits. So clearly this one is 0, but imagine you say, look, this is my virtual address space, right? And I'm saying everything has to be mapped from 0 to 4 megabytes. So the first 4 megabytes have to be mapped. So you say, so page 0 clearly has to be mapped, right? But you say how many pages do I have to really map, right? And you say, okay, what is this 4 megabytes? It's 4 megabytes is 4 multiplied by 1024 multiplied by 1024, right? You can make an observation that this is 496 bytes, or this is 1 page, right? And you say, look, what I'm trying to really do, I'm trying to map the first 1024 pages, right? So 1, 2, 3, and so on up until 1023, right? Agree with this? All right. You say, okay, so what addresses will really be mapped? So clearly you say, I know that the page 0 will have 0 here. The page 1 will have 1 here, because this is the address like OX0, and this address will be OX1000, right? This is page number 2. And you can like, you don't even have need this logic. You just say it, this page, virtual page number 1, virtual page number 2, right? And so on. And you say 1 to the 1024, right? You say, okay, so what is this 1024? So how many bits do I need to represent 1024? You say, well, okay, 8 to represent 256, 9, 512, and 10 bits will represent 1024. So you say that the last entry, which I'm mapping, let me just clear up some space here. The last entry which I'm mapping.
I think you're off by 1.
Huh?
I think you're off by 1, right? Because don't you
Okay.
need to go 0 to 1023, which means you can use 9 bits?
Yeah. No, 10.
Well, because 2 to the 10 is 1024, but you could do all ones of 9 bits and get 1023, right?
No, like, look. 0 to 255 maps, it's 8 bits, right? If all bits are ones.
Oh, yeah, sorry. I'm off by 1, yeah. Yeah,
Yeah.
you need 10 ones for 1023.
So, which means that, okay, I mean, I'm trying to teach you like to come to the conclusion so that in the last page, all of these are ones, right? And it will be like 10 of those, right? 10 bits. And you say, okay, I got it. So what I need to construct in my page table directory, this entry, you can say, well, hold on, like it can point, maybe your page table directory, it is at address 0. You say, well, this one will go to page number 1, for example, right? And inside, it's a pointer to the page table, right? Page table, right? So it's kind of like, this is the pointer. Let me use a different color here. This is a pointer to this page, right? Which sits next. Imagine we just say it will be on a physical page 1, for example, right? So it's next to it. So this page is there. I'm just drawing it here, right? And all these entries, you say, okay, so it will range from entry 0, right? All the entries which are involved in this translation, right? They will be ranging from entry 0, like you just quote me, entry 0, entry 1, entry 2, and up to 1023, right? And you say, look, okay, hold on. So what are we mapping here? So we're mapping to virtual addresses starting from 0, 1, and so on until 1023, right? Because this is the same logic. This is 4 megabytes. And you say, okay, then I will put page number 0 here, page number 1 here, page number 2 here, and 1023 will be here, right? Seems correct?
How is that 4 megabytes?
How is that 4 megabytes? Because
Or I guess
because-
that block is 4 megabytes, but every time you add a layer, you multiplicatively can represent more addresses, right?
no, what I'm saying, like the way to reason about it, if this is your virtual, you say, what is the range of addresses which a leaf of a page table can map? A leaf of a page table, right, has 1024 entries, and each entry is 4096 bytes, right, which is 4 megabytes, right? So if I'm mapping them consecutively, starting from 0, 1, 2, 3, and I'm putting 0 here, it means that this one, let me change the color here. This entry point specifically right here, this entry maps to virtual 1. This entry maps to virtual, hold on, it's not virtual. I meant to say physical. Right? So this will go to physical 2, right? And this last one will go to physical 1023, which is exactly what this assignment is asking. It says, okay, please map virtual addresses from 0 to 4 to physical addresses 0 to 4 megabytes, right?
Sorry,
Because
that's page numbers, not like addresses that you're trying there. It's
yeah,
page number 0, page number
those
10.
are those are
Got
page
it.
numbers, right?
Got
Yeah.
it. Yeah.
Because this is what we put in a page table, right? We page, oh, hold on, what I do? Yeah, we put page numbers because the rest is flags. And I would appreciate if you say, look, I know, by the way, I will put the, like I was using the format here. So I say page table entry P means present, page table U means user accessible, you can, and page table W means writable. But even this single flag, page table P, is okay. I will be fine without any flags, but just I want you to at least like somewhat understand the flag. Sorry for this here, right? Got it?
Mhm.
And now you say you got this point. So this is the first mapping which is asked, right? Any questions? Oh, Shane is like catching me on the fact that, so what is the right way to write 4 megabytes? Or is it the right way? I thought that you were like commenting on the fact that I'm abusing the notation saying that it's approximate megabytes versus.
Oh yeah, I
is-
guess you could do MI if you wanted to be correct, right?
Yeah, I don't know those details. Yeah, I mean, I'm with you, but we don't
Yeah.
need this level, I guess. I mean, here, you know, when you write something in a page table, you have to be correct anyway. So there is only one correct answer. The hardware interprets it correctly. Okay, this is one mapping. So how can we create the second mapping? The one which is, oh, hold on, my chat is, yeah. What was this? Where's the chat now? Damn it. Yeah, back to chat, good. So what I was, now the second mapping, right? So we created one. So where will be this second mapping? The one which I'm asking for here. This one, which maps 2 GB virtual, 2 GB. It's a chunk of the virtual address space. Right now we mapped this entry, which maps from the first 4 megabytes, right? Which maps from 0 to 4 megabytes. And somewhere in the middle of this address space, at exactly 2 gigabytes, I ask, please map the same, these 4 megabytes to the same physical memory, right? This is physical, right? So how can, which addresses will map this? Can anyone tell me? In this page table directory, where will it be? Yeah, 512, good job, right? Oh, someone was saying, can I interrupt it? Okay, go ahead.
No, I was just saying that.
Yeah, so you can observe this fact that it will be right in the middle of the address space, which means, of course, that it has to be in the middle of the page table, right? You can take it more rigorously and you can translate those addresses, right? And you will understand that this entry is entry 512. And here you can put exactly the same thing, actually. This is the beauty. You say, look, I'm so, you know, cautious about memory consumption that I say I will use the same leaf for these 2 translations. So why not? You say, wow, this goes in a very same page. You don't even, you can create a new page and it's also a valid answer. I will count both of them, but you very well can point them to point to the same leaf, right? That's okay too.
How did you get 512?
512. So
I would have done
I mean,
it.
I use this.
Done it slower.
Yeah. So let me just come over it like
Because
yeah,
2 gigabytes is a 1 in the 32nd. Like it's in the 30, the like highest bit of a 32-bit address, right?
Yeah, okay. So this is the page table directory. And imagine this is your virtual address space, right? So one entry, this entry will map the first 4 megabytes, right? The second entry will map the second 4 megabytes, right? And you say, look, I'm asking you, and it's not drawn to scale, obviously, right? We need to map the 2 GBs, right? Which is right in the middle of 4 gigabytes, right? The entire address space, right? And then you can say, look, I get it. So it intuitively has to be an entry in the middle of this, right? But you can very well just take this address, which is 2 GBs, and split it into 10, 10, and offset, right? Obviously, this will be all zeros, right? This will also be all zeros, but this one will be 512. If you can do the math, but intuitively, you can believe me that if the total table is 1024 entries, right? So, and each maps 4 megabytes, right? You can divide 2 GBs by 4 MBs to get the number. Agree with this?
Okay, yeah. The way I thought about it was 1 followed by 31 zeros and then just like chop off all the 20 extra zeros, or chop off all the 10
that's
bits,
absolutely
and then you get
correct.
512 as well. But
Yeah.
I was just confused how I got that answer so quickly because I was still typing out all the zeros.
No, I mean, I cheated a little bit. It's a magical number, so I just remember. And I mean, maybe I will give you a slightly less magical number, like maybe 3 GBs, right? Which is a little bit hard to arrive right away. So you have to divide 1024 divided by 4 multiplied by 3, right? So what it is, I don't even know myself, but should be somewhere there, right?
Yeah.
So 512 divided, so 256 multiplied by 3, it will be entry. Here we can, this logical works like divided by 4 multiplied by 2 if you want to do the half, right? So it's, but you got the point, right? Okay, good. So, okay, this is clear, right? This question, are there any questions about it? Good. Oh, Elliot, thank you. Okay, good. Process organization. So this question is incorrect. So I cannot ask anything like that because last time the midterm was later in the quarter. So when we looked, we probably already knew about exec, and we knew how exec is connected to the memory allocator inside x86. And what I'm asking here is that how many times you will be able to fork. So I was asking you to count how many pages, when you create a new process, how many pages will get allocated every time, right? But right now there is no way to answer because we don't know it. So I will not ask anything like that on this midterm. Oh, but this is beautiful actually. So this is question number 6. Bob says, and it's really like kind of, I can't ask those questions in the undergraduate class, but I can ask them here. Bob says that he can take x86 and disable the exec system call in the kernel. I'm not going to ask this, okay, don't worry, because you don't know how exec works, but I will ask it on a final maybe. So we'll come back to this. So what essentially he says that he can implement exec at user level. So essentially just says that like you can intuitively, actually I can ask this question. So what it says, okay, let's read it. Exec system call in the kernel. Okay, Bob says that he can take x86 and disable x86 in the kernel. So essentially in the kernel, there will be no exec. But he still will be able to execute new programs by implementing exec entirely in user space. Alice doesn't believe him. Help Bob to design the user level implementation of exec. Be specific and justify your answer. Provide a code sketch with comments and explanations for what you're doing. You can assume that you can write and call simple assembly functions that follow normal calling conventions if you need. For example, the assembly function below grabs 2 arguments from the stack and calls the function foo. On the new stack. stack address by first saving the function into the in the EX register and then setting the new stack, moving the stack address into ESP, and then calling the function save in EX. Okay, so what I mean here is that this function call a new stack essentially says this will be a new stack address and this will be a new function. And imagine you're running on this one stack and you say, I want to invoke function foo, but I want to provide a new stack. And imagine that you will run foo on this stack, meaning that the foo will be using this stack. Why is it relevant here? Because this is probably the way to say, look, I want to run something on my stack. I will completely like destroy my address space, but then eventually I will run main on another stack, right? So does anyone have an idea for how to solve this? Like, can you implement exec in user space?
I think we can, but I think the stack needs to be executable for this to happen.
Okay, give me a sketch. So what is needed? Give the sketch for everyone.
As in, can we read the binary into our stack into a variable and call the start of it from the stack?
I believe you can.
You can, but you don't even have to do this, right? So let me give you a sketch. So imagine this is your address space. And you execute some kind of foobar. And this is foobar text. And this is foobar data, right? And imagine this is foobar even guard page. I don't know what to do with the guard page because that requires remapping of the guard. And this is a stack, right? And you say, look, I wanna reload this with the text of a different program, right? And maybe this text will be slightly bigger. Maybe the data will be over here as well, right? And maybe the stack will stay the same, but just for the argument of like generality, let's move the stack as well, right? So this is after exec, right? Agree? You're running right here. You say, look, I will execute some library code which says user level exec, right? And you pass a file name like foo, or like, I don't know, I don't know, what do you want to call this? Let's call it WC, right? Right? This implementation of this user level exec, it can say, look, I will temporarily allocate additional space on the heap. For example, you say, maybe you already had some heap over here, right? You say it will SBRK even more space here. And this has to be executable, as you say. It can say, okay, look, we got it. So I will copy some kind of a tiny trampoline into this area. So I will copy it. And this trampoline will survive the exec. So I will copy it here. I will put it here. And I will maybe create a new stack on which I want to execute this trampoline, right? So stack number 2, for example. This one was number 1. At this point, you say, look, if you have this primitive, which I provided you, so kind of execute on a new stack, you start executing your ul exec, which you copied here, and you say, look, maybe I have to relocate a little bit, maybe ul exec. Maybe ul exec is an assembly sequence that if you're careful enough, you might write it without any relocation. If you have to relocate, you can explain me how you can do this. But ul exec is now running here, right? And it's totally fine, right? At this point, you say, look, I'm running here and I can implement the logic of exec. The logic of exec is to essentially bring this data from disk to memory, right? Agree with this? And you can simply do a read system call, right? Agree with this? Yeah. So you can at this point you can say, look, I will simply start doing read and the read will gradually buffer by buffer will bring the data. Like I will implement a tiny elf loader. So maybe, and it's more ideal. So you can allocate even more space with SBRK, this red space over here. Let me just draw it here as well. This is where you will read everything from an elf file, right? It will be elf header, will be the data section, will be a text section. Then you will implement a tiny elf loader. So essentially at this point you say, I'm not going to execute any other system calls. So if my libc library is somewhere over here, it's okay to override it because I will never execute a single system call again, right? Because if you override it and try to execute libc, then you might get screwed. But at this point you say, look, I will just copy this data into the memory, right, where it has to be. It has to be in this blue address range. So let's copy it right here, right, with memcpi. We'll copy the text here, right, with memcpi. We'll create a new stack. We'll just set the ESP to this, right? And at this point you say, look, I will again execute main, or the entry point of this elf file, whatever was the entry point. And the entry point will be somewhere over here, for example, right? And you execute this entry point on the new stack. Of course, you have to be clever about it. And this is last year I covered how exec works in class. So that's why it's a little bit, I can't ask this question this year, but I'm not going to ask it, don't worry. Because last year we talked about exec and everything what I was explaining, it was already like more familiar, right? But also you have to essentially like create some arguments on the stack, this argv-array, and also put the return address like we just explained in this previous exercise, right? So dummy null address to make sure that, main can access its own arguments. But roughly this is the sketch, right? And I mean, I will take different answers, but they have to be on topic. So I will not take some generic blah, 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 right? But if you can draw me those diagrams, or you can explain how everything will work, or give me a sketch of code, then you score correct answer or partially correct. So
this requires the text section also should be writable, right?
Which section?
The text section to be writable.
Correct.
The text and the data section.
Yeah, you're absolutely right. And in xv6, it's actually writable. The only non-writable page in this in xv6, and again, it will become clear next week, so because we were going to spend a week on the midterm, the only non-writable page is a guard. And that's why you have to say, look, you have to still add an additional system call to xv6 to essentially unmap or change permissions, kind of like say, like, I know where the guard page is. I can compute it by saying that I am looking at my ESP. I know that in xv6 the stack is one page. I will round it down to the next page. That's the guard. So invoke a special system call which remaps, which essentially changes the permissions on the guard page. But all the other pages are in xv6 at least are executable and writable. But this is a very good question. Again, you deserve a point on whatever, if you're on the edge of the grade. I mean, and I'm actually surprised that so many people are so knowledgeable. That's quite pleasant.
Does xv6 have mmap?
It doesn't.
Okay, because you could get around like having to overwrite your own address space, right? With like mmap and map fixed. You could just request the right addresses that the segments want to be loaded at.
But you still need a little bit, like you cannot map. You probably can play these games, but since there might be some additional sections which you have to skip, I argue that you need to implement this simple loader which will read this into memory, and you parse the ELF file and then just process the loadable sections correctly like you did in the forward.
Yeah.
But just, I mean, my goal with this question was kind of like question like it changes the perspective, because I say, look, everything has to be implemented in the kernel, and suddenly I provide a system called exec, which seems to be at the very core of the operating system interface, and it looks that this one has to be can actually be implemented at user level, right? So it can be crossed out from the x86 set and like implemented as a library functionality, which is cute. I mean, I don't think I'm wrong with anything. I mean, it's a nice project for extra credit, actually. Why not to do this, right? For the like at the very end of this quarter, if someone feels like I don't want to do an exam, I would rather do an extra credit project. You know, we can assign some.
What if I already did it?
You already did. It's okay.
I did it in Rust.
In Rust. Okay, good. Yeah, talk to us. So you did this exact in Rust?
It's getting there. It's fairly simple, but yeah, it parses an ELF file and maps the loadable sections, and then just calls mem transmute and jumps.
Yeah, excellent. Right? Yeah, we'll take it.
Cool.
Don't really release it to anyone else.
Yeah.
Yeah, but we will get there. So okay, but we are at 6:20, right? So I'm in a mountain time zone, but are there any quick questions? Otherwise, we'll wrap up. You will go with your other classes. But as I said, don't worry, don't panic. All the questions are logical. We do make mistakes sometimes, so maybe we'll put up some kind of a Slack to ask questions just for this exam. Or maybe Piazza, probably Piazza, just will be watching you. Okay, good. Or anything needs clarification. I mean, I'm sorry we ran out of time, but I will hold office hours tomorrow. So please, if you have any questions, like, you know, you looked at the lectures and you say, I still don't understand, I will be happy to answer tomorrow. And I think my office hours are at 2:30. I got it wrong last time, but no, I mean, I'm there. So 2:30 to 3:30, right before your classes start, right? So it's the same Zoom as the lecture. So I welcome everyone. So and I will spend time there. Okay, good. Okay, thank you guys. I'm not gonna see you obviously on Wednesday, but I wish you luck and I hope everything will go smooth. If anything is wrong, just ask us on Piazza, we'll figure it out. Yep. If you need any special accommodations or you can't make this time, again, contact us, we'll figure it out. But other than that, thank you. Have a good night.
Thanks. Bye.